Today at AutoFix Pro, how to check ABS sensors. Inclusive test instructions for wheel speed sensors 3rd generation. For more car facts, automatic, transmission, Audi's S-Tronic, dual clutch gearbox, and other stuff, check out my YouTube channel AutoFix Pro. Wheel speed sensors, which are used for the anti-lock braking system and other driving safety systems such as ESP, ACC, and others, are distinguished as passive and active sensors. Passive sensors have almost completely disappeared in modern vehicles, as they no longer meet the requirements of modern driving safety systems. The distinction between passive and active is not always visually apparent from the design. The distinction based on the designation is determined as follows. Passive. The sensor operates without applying a supply voltage. Active. The sensor is activated by applying a supply voltage. In this video, I will cover the following topics. Difference between passive and active sensors. Electrical circuit of the active sensor. Structure of the sensor. Signal types. Testing options in practice. The passive sensor generates an alternating voltage by rotating the pulse wheel, the level and frequency of which depend on the speed. Red curve, low speed, low amplitude, and low frequency. Blue curve, high speed, high amplitude, and high frequency. This also results in a disadvantage of this sensor. The control unit can only detect a sensor signal above a certain speed because the voltage is too low when the wheel or vehicle is traveling at very low speeds. There are different generations of active sensors. The first active sensor could only detect the speed from a standstill. The sensor consists of an electronic circuit with an operational amplifier. The rotating sensor wheel changes the magnetic field in the sensor. This causes the electronics to switch a resistor on or off internally so that either 7 mA or 14 mA flows. This change in current causes the ABS control unit to detect a change in voltage in the control unit, enabling it to immediately detect movement from the first tooth and calculate a speed. Testing the passive sensor is relatively easy to do. To do this, disconnect the plug connection to the sensor. A resistance test can be performed on the sensor. The resistance is usually between 700 and 4,000 ohms. If the sensor wheel is turned past the sensor, an alternating voltage can be measured with the multimeter. The frequency and voltage increase with increasing speed. The sinusoidal voltage can be visualized with an oscilloscope. Since these sensors have not been used since 2008, I will not go into further detail. The first generation of active wheel speed sensors consisted of a transmitter with a Wheatstone bridge. This consists of 4 magnetoresistive resistors. This means that they change their resistance depending on the magnetic field. There are also first-generation sensors that work on the Hall effect principle. However, this is irrelevant for testing these sensors. The applied supply voltage, usually around 12 volts, causes a voltage drop at points 1 and 2. If all resistors are equal, the voltage between points 1 and 2 is 0 volts. The change in the magnetic field alters the conditions in such a way that the voltage between 1 and 2 changes, in the form of an alternating voltage. This is processed in the OP amplifier, and a resistor is switched on or off so that either 7 or 14 milliamps flows. The control unit contains a measuring resistor at which a different voltage drops depending on the current. The voltage at the sensor is therefore recognizable as a square wave signal. However, this only changes by approximately 200 millivolts. Here is a table showing assumed resistances to explain Wheatstone's bridge. The supply voltage is 12 volts. The voltage UX changes depending on the resistances, which are influenced by the magnetic field. Since the magnetic field does not change abruptly, the resistances do not change abruptly either. This results in an alternating voltage between points 1 and 2, i.e., UX. This cannot be measured because it is processed in the sensor by the internal electronics. The speed signal is transmitted as follows. The sensor is supplied with a supply voltage, usually 12 volts. The sensor limits the current through the internal circuit to I low equals 7 milliamps or I high equals 14 milliamps, depending on the position of the encoder wheel. This changing current generates a changing voltage drop across the measuring resistor Rm. This changing current generates a changing voltage drop at the measuring resistor Rm. URM. The control unit uses this signal to detect the speed. The resulting minimal change in sensor voltage, U sensor, can be visualized with an oscilloscope. I will discuss further possibilities for signal evaluation later on. Description of the sensor circuit. U sup, supply voltage. U sensor, operating voltage of the sensor. URM, signal voltage at the measuring resistor in the control unit. RM, measuring resistor in the control unit. I low and I high, sensor current. In addition to the rotational speed, the current wheel speed sensors can also transmit the direction of rotation, the installation position, and the air gap reserve. This is done via internal evaluation electronics integrated in the sensor. The image shows that the sensor consists of two Hall sensors. As the sensor wheel passes by, the Hall voltage is changed first in Hall sensor 1 or Hall sensor 2, depending on the direction of rotation. The sensor uses this to determine the direction of rotation. At the same time, the air gap and the installation position of the sensor can also be determined. The image on the right shows the different signal shapes. At the top is the signal from a single Hall sensor, which is transmitted to the internal evaluation electronics. The second image shows the output signal from the speed sensor at standstill, which is evaluated by the control unit. The third curve shows the signal during counterclockwise rotation, and the fourth shows the signal during clockwise rotation. Below that is the signal depending on the installation position. This is output when the magnetic flux change in the Hall sensor is too low. As with all tests, a visual inspection of the relevant components should be carried out at the start, and the fault memory should be read. This includes wheel bearing play, sensor wheel, plug connections, and electrical cables. I also recommend checking the battery, as undervoltage can sometimes cause faults to be stored that are unrelated to the cause. If necessary, check the generator as well. With such a test adapter, measurements can be taken on the active sensor. It is plugged in between the sensor and the connection cable. The supply voltage and the signal can be measured at the two measuring sockets. The image below shows the supply voltage measured on a VWE up with the ignition switched on and the wheels stationary. With a diagnostic tester, the fault memory as well as the actual values can be read out. For further testing, an oscilloscope can be used. There are various ways to make the signal visible. For sensors of the first and second generation, the signal can be amplified. See image on the right. For this, a 100 ohm resistor is connected in parallel to the sensor. The disadvantage is that the control unit usually detects this resistor and registers a fault in the fault memory. However, the signal can usually be made visible using this method. The image on the right shows the signal on a Golf 6 with a resistor connected in parallel and a slowly rotating wheel. Unfortunately, I don't have a picture I took myself of the second generation signal. These signal images look like this. With third-generation sensors, the signal looks completely different. When the wheel is turning, the signal looks as shown in the image on the right. When the wheel is stationary, the speed pulse is not visible. Additional information, such as the direction of rotation and installation position, is transmitted via the serial data protocol, which consists of 9 bits. To make the third-generation signal visible, I conducted several tests with different oscilloscopes. Unfortunately, the results were not really satisfactory. However, with an analog oscilloscope, you can see both signals, one with the wheel stationary, without a speed pulse, and one with the wheel rotating, with a speed pulse. Here is the signal with the wheel rotating. If you look closely, you can see the dots that represent the serial protocol and another, slightly brighter dot that represents the speed pulse. Unfortunately, I haven't yet managed to enlarge the signal. I hope you can still see it. The experimental setup on the right side was conducted with a wheel speed sensor from the rear axle of an Audi Q2. I assume that this also works with other sensors of the same type. I take no responsibility for any possible damage. Instructions. Disconnect the sensor from the onboard network and supply it with a voltage of 9 to 12 volts via a 220 ohm resistor. A 9-volt battery is sufficient for this. Connect the oscilloscope in parallel to the sensor. With a supply voltage of 9 volts, the signal from the speed sensor can be nicely displayed using the Bosch FSA oscilloscope. The signal comes from a removed speed sensor that is not mounted on the sensor wheel. What can be seen is the serial protocol. The bits can have the following meanings. This depends on the programming. Not all bits have to be assigned. The speed pulse bit is low when stationary and high when the wheel is turning. Bit number 0, error bit for air gap reserve. 1. Validity of the signal amplitude of the 3 installed sensors in chip 0. 0 if valid, 1 if invalid. 2. Not used. 3. Validity of the direction signal. 4. Direction bit / rotation direction. 5, 6, 7. Air gap reserve of the 3 sensors in the chip. 8. Parity bit for error detection. Here is a video of the signal at a standstill. In between, you can see a few times the high signal at the beginning, which appears when there is a small movement. This means the wheel is moving. In between, you can also see changes in the signal while at a standstill. Here, I moved the speed sensor further from the tone wheel or closer to the tone wheel. In the next video, I will show the speed signal during forward and reverse movement. Here is the video of the wheel spinning. The speed sensor is on the right rear wheel. In the video, I start by rotating the wheel clockwise, i.e., forward motion. Then, I change the rotation direction to reverse. The difference can be clearly seen on the 5th bit. Later on, I change the rotation direction 2 more times. Warning. During the test, I found that 9 volts is almost a bit too low. Either use a 180 ohm resistor or a new 9-volt battery. If the supply voltage is slightly too low, the following error signal appears when turning the wheel. With another sensor, the signal looked slightly different. However, the data protocol was also missing here. To test the magnetic sensor wheel, there are special cards that can be used to visualize the magnetic field. There are also sensors with a permanent magnet installed directly on the sensor. In this case, the magnetic sensor ring is not used and a gear wheel is installed, as with the inductive sensor. There is also a special testing device for checking the sensors. Thanks for watching. More videos on my YouTube channel AutoFix Pro.